let's wait for a few more minutes so that anyone who is joining can come in. Okay. I think we should get started. I hope I'm audible. Hello everyone, I'm Ayush Kumar Tyagi. I'm PhD student at IIT Delhi. Work in intersection of medical imaging and AI. In today's session, we will be looking into uh, object detection problems, and we will conclude by segmentation task. First, we will look into few of the problems, and then we will go about seeing things in like working. We will look into few of the detection libraries, and let's see and we'll see what kind of problems we can solve using object detection and segmentation tasks. Right, let's get started. So question number one is, which of the following statement uh, distinguishes between object detection, classification, semantic segmentation, and instant segmentation? Right. So just to put things into context, right, for a given image, uh, there can be many things present in the image, right? Like suppose you are taking a image of a street view, right? Like this is from US street view. You can actually design multiple tasks around it. So one thing is basically you are uh, suppose you are working for like this NHAI, National Highway Authority of India, and there are 3 lanes in your new highways, right? and the first lane is basically for trucks. This is These two lanes are for cars, right? And your first task is basically to identify whether any truck is traveling in these two lanes, right? So there you can actually approach the problem into multiple ways, right? So you have some camera installed at this point, right? And what you will be doing is, like, at random instances you will be taking snapshot of the camera and see what like scene it poses, right? So suppose there is a car which is coming here, right? You can propose this problem as a classification problem as well, and object detection problem as well, right? So you'll take the snapshot of the scene, and your objective is to identify whether there is a car or truck is present in that in this scene. So you suppose you only take picture of this, your camera only give you this portion, right? Or maybe this portion. So in classification tasks, what will be you will be outputting, you will say whether there is a car present or there is a truck present, right? If there is a truck present, then there is a violation of whatever rule we have set up, right? And you inform the authority that near this uh, camera, near this intersection there is a truck which is passing through, and the truck is basically going in lane 1 and lane 2, right? So this you can actually pose it as we are actually posing it as classification task. Similarly, we can actually pose it as object detection task, where I am actually using bounding boxes to define where the truck or car is present in the road, right? And since I'm actually able to uh, localize the object, I have a better understanding of its motion, its attributes, and I can actually make better inference or sense out of that. So uh, so the major difference is, basically, given an image, you are actually looking into just labels, where you say that, like, car or truck is present or not. It's basically a yes or no kind of a problem. Then it's a classification task, right? And if we are actually interested in localization as well, then it becomes a object detection task. Similarly, extending this, if we are actually interested in a very clear boundary of maybe car or like whatever object you're tracking or identifying, then it becomes a segmentation task. And here also you have semantic segmentation and you have instance segmentation. In instance segmentation, you're saying that, like, if there are two instances, suppose you're actually looking into microscope and you're looking into images of cell, right? And there are multiple type of cells. So what you're doing is, like, you are actually identifying cells by different instances, right? There are four cells of same type, but there are basically four of them, right? So each instance has its own uh, value, right? Semantic is basically you're representing every cell with the same label, but if there are other type of cells also, maybe, right? So then those will have different kind of label or the pixel values, right? So this is the overall like classification of any image processing task, right? And there are multiple applications for this. You can use object detection and tracking as well, where initially you detect an object and then you track the trajectory of this. You can actually extend it into activity recognition task, or maybe like key point attribute detection task, where you have a person and you are basically detecting where are the shoulders is, where are the knee joints are, right? So key points basically are identifying, and similarly you can actually extend it to some sort of a landmark detection task, where suppose you want to build a feature in your phone, and you want to your phone to be unlocked only when you see that it sees your face, right? So facial recognition task. So for that, the first step is basically the object detection. You identify where the face is, and within the face you do some sort of a feature extraction and do the matching with whatever the feature vector you have stored while configuring the face recognition application, right? So the base is actually these three: classification, localization, and the segmentation, and it extends in various applications. In cell segmentation, like in the segmentation in the medical imaging, people use it to identify cells, maybe like tumor regions, or even if you're actually working on satellite images, where suppose you are like looking into the flood detection task. Suppose like maybe uh, yeah, maybe you are working in the meteorology department, where basically you are responsible for predicting the next weather, or like any natural calamities that might be happening. You can actually take satellite images. There can be, suppose, this river, and you have a reference image where you can say this is I1, and what you do is like you segment out the region of the river, and in case of flood in I2, your river like dimension will vary, right? You can actually do again a segmentation task and identify in which direction the river is basically expanding, and basically alert maybe these people or these people, right? So there are many applications in both in localization and segmentation space. Yeah. So coming back to what we were looking into, so the question is like, what are the correct attributes for object detection, classification, semantic segmentation, and instance segmentation? So object detection involves classifying each pixel of an image into specific class. This is basically wrong, right? So it's attribute of segmentation problem. So classification assign a single label to an entire image, indicating the most prominent class. Prominent here why? Because suppose you are uh, like suppose you are looking into a dog classification task, right? And there can be other animals as well, but if you are not interested in other animals, so your prominent class basically become the dog. So you kind of ignore the background whatever it is, right, and only focus on the dog. So the prominent object class, while object detection identifies and localize multiple objects, right, using bounding boxes. So this is correct, right? So semantic segmentation assign a unique label to each object instance in the image, right? So this is wrong, right? So this is, instead of semantic, this is instance segmentation, right? So each instance assign a unique label, ensuring different instances of the same object are distinguished from each other. So this is anyway wrong. In instance segmentation, the goal is to classify and differentiate each instance of an object in an image, while semantic segmentation is goal is to classify each pixel into fixed set of categories. So this is correct. So in our case, B and D are correct. Make sense? So next is basically so whenever we are actually doing object detection problem. So suppose this is image and this is the bounding box our model is predicted. So in order to ensure that like we are actually predicting good, how do we actually evaluate it? Evaluate in the sense like you when you are actually creating a data set, you do annotation in a form of, so suppose for each image there are basically two objects, right? And when what you do is like you annotate these objects with some sort of a ground truth. So these two are object and you basically draw bounding boxes around them. So since both of them actually are the same class, these are and assign a class to each of the bounding boxes, right? So when we actually test this image, so we pass this image to model, and it predicts something, right? So maybe something like this. It did a wrong prediction. Right? So model made some error. So how do you actually evaluate how good the predictions are? So there is one metric which is called as the IOU. So this is intersection over union. So and we will see like how we actually compute the intersection over union. So IOU is basically, suppose A intersection B divided by A union B. So A here is your bounding box B1, B here is your bounding box B2, and you have an intersection of B1 and B2, right? So basically you have, suppose you have two bounding boxes, and right, so this is B1 and this is B2, and this is the intersection, right? And whatever the area is remaining is the union, is along with the intersection actually, right? So what we want is we want to actually maximize this area. So right, and your IOU will be minimum when the intersection between B1 and B2 will be maximum, right? So what is the range of IOU? So when there is no intersection, IOU is basically 0, right? Because intersection is 0 and 0 by anything, right, doesn't make any sense, so it's 0. So when there is 100% intersection, then IOU is basically 1, because B1 and your B0 basically completely overlaps. B1, B2. So B1, B2 basically completely overlap, and intersection is basically complete bounding box, and union is basically the complete bounding box. So intersection and the union are same. So that's why your maximum is basically 1. So anything between 0 and 1 is the range of this metric. So now we will solve a question regarding it. So suppose you are given two bounding boxes. So this is first bounding box A, and the coordinate in the image plane are 2 comma 4, and the bottom coordinate is 8 comma 10. There is another bounding box which is 5 comma 6 and 12 comma 14. So this, let us see if we can somewhere middle. 5 comma 6 and I guess 12 comma 14, and we want to compute the intersection over union for this idea. So let us see, first we compute intersection, so A intersection B, right? So we want to compute what is the area of this region, and the area is basically uh, difference in width and height, right? So 5, 2 by 3 by 20, let us see, by 20, I think is the right answer. Let us see, uh, 10 minus 6, 3 into 4, right? This is 12, and union is basically uh, this is the area of A, area of B, and then we will simply subtract whatever we are adding 2 times, that is the intersection of A into B. So it will be area of A plus area minus area of intersection A intersection B, because we are adding it 2 times. So it is 8 minus 2 into 10 minus 4, 6 into 6, 36. And intersection is so it actually become 36 plus 56 minus 12, 92 minus 12 is 80. So answer is basically 12 comma 80. So we can actually remove 4 and 3 comma 20 is right answer. Yep. Right, and what we want, this is basically closer to 0, but like right, but what we want is we want to actually maximize, so this intersection has to increase if you want to do good predictions. Any doubt in this, or shall we move ahead? Okay. So in object detection there is one famous uh, library which is called as the Yolo. That is, you only look once. This is basically a class of single shot detection. You directly predict the bounding boxes. Right. And there are multiple variants of Yolo. So it started with Yolo, and then V1, and there are multiple. Then V3 was very famous because it was very fast. And then it was, so the latest is basically Yolo V11. So we are at 11th version of this object detector. Right. So let us see like what are the which statement is basically true. So Yolo V1 loss function primary focus on, sir, I think there is 12th also. Yeah, maybe the recent one is 12th. Yeah, but I have used till 11th, I guess. And so, yeah. So YOLO loss function primary focus on regression on bounding box coordinates, heavily penalize small localization error, but struggle in detecting small objects due to grid cell constraint and equal weight of each class and localization loss. So let us see what is happening in this case, right? Suppose you have this image and this is you're solving that a task the task of object detection, right? So whenever you get an image, you place that image into multiple grids. These are the grids. So basically we are dividing each image into multiple uh, grids, and we will be doing analysis on each grid. So for each grid, while uh, yellow dot is basically defining the grid, and this is basically the grid center, right? For each grid we are making some prediction. Suppose there are each grid we will make two prediction, and we'll try to predict if there is the object which is centered around that grid, right? And we will try to maximize the like intersection over union for each predicted bounding box. Right? So what uh, like what we do here is we have like we are basically predicting bounding boxes, coordinate of bounding box. So these are x, y, width, high coordinates, and also we are predicting how confident we are about the prediction. So some sort of a confidence score also we are predicting. Additionally, we predict the classification score also. Suppose you are actually doing object detection on 10 classes, and we are trying to predict which class this bounding box is bounding box belongs to, right? So like you have for each like cell or maybe the grid, you are predicting bounding box and some sort of a look like confident information. So the loss is basically this is your localization loss. So this is x1 for each coordinate in x plane and y plane. So basically you are computing, suppose this is the point x comma y, and this is what you are predicting x dash and y dash. So I'm just trying to minimize this distance, so I have to compute what is the error in my prediction, and this will actually act as a loss function for us. Then we have confidence score, right? This is also called as the objectness loss. And then the third one is basically the classification loss. So in initial version, people are actually using the cross entropy as the classification loss, and the issue is with cross entropy is that it doesn't weight like different class differently, right? So like in case there are a lot of backgrounds, these models were actually making very like many errors when things were crowded, and maybe in the cases where the images or objects are very small. So in those cases, model was actually making good amount of error. So which was later basically like corrected in the later version, but initially it was making error. Yeah. So initially, so in the first version, what we were doing, they were actually trying to predict the bounding box coordinates. Um this was um basically like focused on so localization error, but there was since there was like a class imbalance, they were actually not using some sort of any weighing mechanism for each class, right? So this statement is actually true. So next is basically we're talking about YOLO V2. So YOLO V2 basically introduced anchor boxes. So let us see what was the anchor boxes. So in version 1 we were actually trying to predict these coordinates x, y, width, height. X, y, maybe this is the width and this is the height, right? But initially when we start training, right, we don't have any good indication of what these coordinate can be, right? So initially we were making lot of error, so the training initially was very unstable. So what people actually thought that, like, let us initialize or like help our detection model by providing certain anchors. So these anchors are define how does the typical object shape actually look like. So if you are actually looking into what say maybe car or truck detection, so the bounding box around car will be something like this, whereas the bounding box around truck might come out to be in this shape, right? Slightly higher in height. So what people thought, like, let us provide what are the common bounding box that can occur uh, during the task as priors and help our detection model. So this YOLO V2 and like after that also people actually started providing bounding boxes as a prior, and these bounding boxes are called as the anchors. So YOLO V2 actually introduced these anchors. But what difference does YOLO V2 made? So whenever there is a prediction for each grid, suppose this is P, this blue is basically your predicted bounding box, and this dot is your anchor. So instead of like directly predicting the what do you say your coordinates, these model were actually predicting the shift from the anchor only this distance maybe. So what is the difference in the maybe width, or maybe what is the difference in the height, this distance basically, and width, this and this error, right? So instead of directly predicting the localization, they are actually predicting the like relative error, and that makes actually training like stable and provided better localization. So it did well in that case. Yeah. So provided anchor is true, right? But continue, it says it continued to use the same loss function as YOLO v1. So there is a change in the loss function, right? And there was a change in the classification part as well. So the loss function actually they modified based on the kind of error we were getting in YOLO v1. So this is actually not a correct statement, right? So next is basically YOLO v3 improve on YOLO v2 by using multi-scale features. That is true. And binary cross entropy for classification, which reduces false positive in dense environment. However, YOLO 3 abandoned uh, the anchor losses, right? So this is not true, right? Anchor based like task actually continues till I think even the latest one. So and YOLO V4 incorporates innovations such as this darknet. The darknet is basically a very optimized model, which is I think was implemented in C. So it was very good for real-time application. So yeah. So and other type of activation. So mosaic data augmentation is, let me just explain what is. So there can be different type of data augmentation. So there is typically crop, rotation, flip, hue, saturation, exposure, and aspect ratio, basically width and height, right? So these are basically uh, changing the way your images look like. These are basically changing how the images were taken, right? Some sort of a rotation. Or cropping is basically you only take few part of the image, like something like this. Rotation is what is happening here, and flip basically horizontal flip or vertical flip, right? So these augmentations people were actually using. So later there were multiple type of augmentation which were introduced. So one was mix up. So you basically mix two images. So this is image 1, this is image 2, and your mix up between two images basically lambda 1 times image 1 y minus lambda times image 2 basic. So your image is basically mix between two images, and similarly the labels between them also are mixed. So suppose this is a classification task and there is a label c1, right? So lambda times c1 plus 1 minus lambda times c2 will be the label, and if this label is greater than certain, suppose zero. 0.5, you assign it to c, maybe c2. If it is less than, then you assign it to c1. So this was mix up. Next is cut mix. Is basically you, for an image, what you do is you cut a small portion of this image and place it in this image, right? So why people do this? Suppose I have an image where there is, suppose you are actually looking into some sort of a, maybe you are actually looking down the microscope and identifying whether your, suppose you have a histopathology image where you can actually see the cells, or maybe you're actually doing some sort of a blood analysis, right? And you there are mostly one type of cells are there, right? And you are interested in these type of cells, right? Or maybe the object, and these type of objects are very rare. So how people actually increase the data set? So what people actually do is they just take out this region and paste it in multiple images in various places like this, and where other cells are like this, maybe here, maybe another. So that's why, so this, in this way you're actually increasing uh, the chances the model is seeing this type of objects, so that like the now the when model is basically predicting, it's more confident. So cut mix is that. So you cut a portion of another image and paste it in another image. So this is a cut mix. So what Yolo actually does it. So what? So it takes multiple images. So this is image 1, image 2, image 3, image 4, and combine them into forming it one images, or like it can actually take multiple region of a image, right? Suppose this is from image 1, this is from image 2, maybe this region from image 3, and maybe this region from image 4, and then place them and like combine them into forming a like single image. So now you have multiple objects which are present in the image, so we are kind of mixing whatever the original distribution was. So you are seeing these minority classes more now. So they actually introduced this data augmentation. So Yolo v4 did this data augmentation, right? And they improved the class balancing with the balanced class localization and objectness loss, and they also used CIOU. So let's talk about what is CIOU. So we have seen that there is, before going to CIU, there is a basically a trajectory of what previous methods were and what are the basically the possibility, or like what are the demerits of those methods, right? So we will look into it. First one was generalized IOU. So first one is basically IOU. Maybe second is GIU. So IOU is, what is the issue with IOU? Suppose there are two bonding boxes. This is B1, this is B2, right? So IOU between these two boxes is 0, right? Then if you look into these in this case, where the predictions are actually much better. So suppose B1 is your, what do you say, prediction, and B2 is your ground truth, right? So what we want B1 to be as close to B2, right? Like they should be overlapping. Whereas what is happening in first case 1, they are very far apart. IU is basically 0. In case 2, what is happening is it is slightly better. So B1 is basically predicted closer to B2, right? But uh, IOU is basically still 0. Right. So what we are trying to do here is, we are trying to, how do we actually tell model that like in case 2 is actually better than case 1? So we do not have any indication of that, right? So IOU as a loss function is not providing that indication, right? So we need some sort of a mechanism which can actually tell that case 2 is actually better than case 1, right? And how, before that, how do you actually use IOU as a loss? So loss IOU is basically 1 minus whatever the IOU you are getting, right? We try to minimize this loss. So coming back to generalized IOU, so the issue was we don't have a mechanism of telling a model that case 2 is actually better than case 1. So what generalized IOU does, it also take the minimum bounding box which can surround both the bounding boxes. So A and B are two bounding boxes, and I want to draw a bounding box around A and B, so that like it is the smallest bounding box that surrounds both A and B, right? And this will be minimum when A basically intersect with B, and B, like, and both of them basically intersect with C, right? Then your basically your loss is 0, your GIOU is basically 1 at that point of time. But now what we can actually do is we can actually provide a better indication how far the bounding boxes are, right? So suppose you want to draw a bounding box around them, you actually will draw something like this. In this case, you actually draw something like this, and so we can actually say this is basically better than this, right? So this is a basically a better metric when you are actually computing intersection over E, right? So if you can actually see in the image, so intersect IOU is 0. So the gradient we will get at this point is basically 0, right? So here also IOU is 0, gradient will we are getting is 0, right? In this case there is some IOU, so it's basically 0.42, and you will have some gradient to actually back propagate. In case of GIU, we have a signal because GIU is giving us some value, right? Minus 0.68. As we move to case 2, GIU is giving us a value of minus 0.23, so which is basically saying that we are actually moving in the right direction. And finally, your value is basically point 39, which says that like yeah, we are moving from like very negative to a a positive value, right? And we want to keep on improving it to one. So essentially what we are doing is we are telling model in which way it has to predict bounding boxes. So it works well. uh, However, suppose you have two bounding boxes which maybe your uh, maybe your ground truth is red and your prediction is green, or other way around is also true, right? So what we want is we want to align this green box at the center of the object, right? So in this case we are not aligning, in this case also we are not aligning, but this case this is well aligned. But in all the cases GIU is basically 0.75, like that is basically equal to your original IOU, sorry, loss. Basically we are actually computing loss, but anyway, right? So this is the issue, right? Like if two boxes are overlapping, and then we don't have an indication that in which way is a better alignment. So what people use is basically come up with distance IU. So what they do is, suppose this is the center of box 1, this is the center of box 2, and what they do is like they compute the distance between this center 1 and center 2, and they try to minimize this distance as well, right? So this has a minimum distance. Here also there is some distance, but we can actually tell this is actually a better, so distance is basically greater than distance 2. Here also the distance is basically d3 is actually 0. So we are actually moving in a better aligned bounding boxes. So the next is basically the complete IUU. So it takes GIUU plus distance IUU and solve the only thing that is remaining was the size of bounding boxes. So what it actually does is that this diagonal between this bounding boxes should be basically of same length, right? So the aspect ratio basically should be same, your width and the height. So and it aligns based on that. So in this case you will be center aligned, in this case you will be aspect ratio aligned. So that's what complete IOU does. So I think if you have an option, just use CIOU directly. I think it should be available in PyTorch, and I don't think it is difficult to implement as well. Yeah, so like fourth option is also correct. So the correct is A and D. any any doubt at this point, or is it like too much? Or okay. Next we will look into focal loss. So we know what is cross entropy or binary cross entropy, right? So but there were coming up there were certain problems where there was one class as majority and the other class was minority, right? So you'll see most of the samples from like majority class, right? And the model only focuses on correcting your majority class, right? And completely ignore whatever the loss or whatever the things that corresponds to the minority class, because your majority class actually corresponds to the majority of your loss, right? And if you are actually correcting that, then it gives a signal that you are actually reducing the loss. Whereas when you actually deploy it in the real world settings, you make error in the cases which are very less frequent, right? So what we want is we want to identify what is the false statement. And so there is a paper called focal loss for dense object detection. This is by fair Facebook, and this basically introduced this focal loss in 2018. And these figures are basically from the paper only. So what this figure is basically showing is your loss is actually in this form: minus 1 minus p uh, log p, right? And there is some factor which is gamma. So what is happening in the let us say the original cross entropy, uh, right? So what we are trying to do is we are trying to maximize the probability to 1, and there is majority class which has suppose maybe 10,000 samples, right? And we, in most of the cases, you are kind of predicting the maximum probability, or predicting it to be close to point 0.8, right? uh, so but still, right, you want to push it to 1. So what is the error you are getting? So the loss at this point is 0.2, and if you multiply it with 1000, you get 1000 as the loss function, the value of the loss you are actually still incurring, right? But pushing point 0.8 to to 0.99 or maybe 1 is not going to help, right? Anyway, anything above zero point 0.5 is anyway class 1, right? So if you keep on only focusing on this loss, that is a huge quantity, 1000, right? So this is actually not going to help your model. So the cases where suppose you are predicting maybe zero point 0.3 or maybe zero point 0.4 will be, are the basically hard cases, right? These are the easy cases, right? So suppose you are basically predicting for 0.4 and so all the majority minority classes you're making error. Suppose that's what is happening. So you are maximum predicting the probability to be zero point 0.4, and there are suppose maybe 100 cases of that. So your loss actually become 10, right? So the model, and the loss for the majority class is 1000. So model is basically focusing on this to reduce this 1000 loss, and completely ignoring this loss due to minority classes, right? So what we want to push down the effect of this loss, and focus on the minority classes, right? So that's what uh, focal loss does. So this gamma factor, right? So this gamma factor is basically reducing the loss, right? Suppose at zero point 0.6 this is close to maybe 0.75. With gamma 5 it is basically close to point maybe 0.02 or something like that. very close to 0, right? So the cases where we are already doing good, we are computing very less loss due to this gamma factor, right? And we are focusing on the cases points where actually we are making errors and considering this region actually, right? So uh, right, so there is one gamma factor, there is something called as the alpha factor. So alpha factor actually uh, assign different weight to each class. So suppose there are maybe 10,000 sample in class 1, and there is class 2, there are 100 sample. So what alpha can be is like maybe 1 upon 1000 is your alpha 1, and 1 upon 100 is maybe your alpha 2, right? So for each class you are assigning different weight in the cross interval. So coming back, so we have to identify which is the false statement. So Foucault loss applies a scaling factor to standard cross entropy loss to reduce the relative loss for well classified example and focus on hard samples and misclassified examples. So this is correct. Increase in the value of gamma in the focal loss will reduce the loss contribution for hard examples, right? So this is wrong. So it will reduce the contribution for easy examples actually, and right, so that the model can actually focus on hard examples. So this is wrong. So this is the false statement. Next is parameter alpha in the Foucault laws is used to address the imbalance in the classes, giving more weight to minority class, right? So this is true. Focal, Focal loss is particularly effective in scenario where the significant imbalance between number of foreground and the background objects. So this is also foreground versus the background is also a imbalance problem and majorly seen in object detection task. So this is basically true, and in fact the focal loss was actually introduced for object detection task, right? So B is basically incorrect. Any doubt in this question? I think there are two more questions. We'll quickly like rush through them, and then I think we'll go to coding part. If you have any doubt, just put in the chat. Which of the following statement is true regarding the two-stage object detector? So there was Yolo was a single shot detector, so single stage detector, and there was another class of detector which were actually running. So this was two-stage detectors. So first they actually identify features or like region proposals, and then they identified whether there is object present in that region based on some sort of a classification mechanism, right? So this was like they started with the region RCNN, then moved to fast RCNN, then faster RCNN, right? So this is the like architectures from all of for each, right? So this is RCNN, this is fast RCNN, and this is faster RCNN. Right. So in fast, so normal RCNN, what do they do is like given an image, they extract out regions. These are basically they call it as the region proposals, and they pass everything into a classification CNN based model to extract out feature, and then a simple SVM to basically classify whether uh, the category or the class is present or not, and then you have a regressor as well which is basically predicting out your coordinates. In fast RCNN they actually use a deeper architecture. So they from the bounding box they actually extract out the feature map, they map it to a feature map, and then use that feature map to actually classify whether the object contains the category which we are interested in, right? The faster RCNN, but this in this case also we are actually looking into different like region proposals, right? And that actually makes things difficult. So what faster RCNN does is basically they you take the image, extract out features using a CNN based layer, and this is basically the end-to-end trainable thing, right? So only thing that makes it very good is this end-to-end trainability, right? So you have a region proposal network which extract out what regions one can be interested in. So maybe these three regions are there. Then based on this region proposal network, you actually extract out what are the region proposals and only send those region proposals for classification task to see that there is a object present or not in that, right? So this is basically the increasing order of speed and performance also. Yeah, so we have to identify the true statement. Fast RCNN improve on RCNN by integrating the region proposal step into the network, eliminating the need of separate selective search algorithm. So both faster RCNN and RCNN use selective search algorithm. So this is incorrect actually, right? Faster RCNN improves uh, upon fast RCNN by introducing region proposal network that shares convolution features with directed network, making object detection end-to-end task. So this is what we are talking about, region proposal network. So this is a true statement. In fast RCNN, faster RCNN, the region proposal network generate object proposals directly from the raw image without using any CNN features, leading to the fast and more accurate prediction. So actually, this fast region proposal network is fed with some CNN layers, and this is end-to-end trainable. So it's not directly uh, that we are actually feeding the image; we are basically feeding the features. So this is actually incorrect. Both fast RCNN and faster RCNN use sliding window approach to generate region proposal, but faster RCNN region proposal network generate high quality proposal, reducing the overall time. So faster RCNN don't use any this sliding window approaches. We are actually directly predicting the region proposals. So the answer in this case is B. So the last question is basically regarding the segmentation. And there is one very like uh, famous architecture which is called as the unit architecture, and I think it was introduced in 2015 for biomedical images in the microscopic images for cell segmentation. So, this basically the architecture looks like U. That's why the name is unit. So what it does is you have the image. Suppose you have 572 cross 572 image, right? And right. So this is basically one. So it is actually because these are the grayscale images. So they were actually using grayscale images. That's why the number of channels is one. But ideally, whenever you are training on natural images, it should be three, something like that. If you are actually training on satellite images, it's more than three, maybe 11 or something like that, right? So what they do is like they apply these CNN layers, do max pooling, right, reduce the size, again apply CNN layer, increase. You can see that there is an increment in the number of channels at each step, right? So they are looking from extracting local to global features. Because when you map each pixel back to the original form, suppose here this becomes slightly bigger circle, here also it becomes slightly bigger circle, something like that, and again if you map it back it becomes slightly this bigger circle. So this is basically called the receptive field of a pixel, right? So you at this point you're actually looking at a very big region to extract out features. So what they're doing is they're actually going from local feature to global features, and then they use this upsampling convolution operation to move back to the original shape, and this your segmentation mask will have generally the same dimension, but number of channel is one because it's anyway like a single classification task. You can actually have two channel also, like suppose one is for completely you're just predicting black, the other you are where the object are you're predicting white. These are white pixel, so here it can be 255 pixel values, something like that. But like generally people do with the single channel because it's a anyway binary classification task, binary segmentation task, sorry. So you have a black, just think of it as black as the background, and these are maybe white or something like, or opposite of also true, right? Only thing is like it is 0, this is 1 or something like that, 0 or 255, something like that, right? But you're anyway, what you generally do is you predict this because you are actually using some sort of loss and you don't want it to be very large, so you scale everything between 0 to 1 and use the cross entropy or binary cross entropy to maximize the probability of the object to 1, right? And then you basically scale. If you want, actually you can actually do some sort of a thresholding, any value greater than maybe zero. 0.5, you map it to 255 pixel value. So that's how you actually uh, like push it into the original space of pixels, right? So this is what is happening in the like segmentation task. You have a unit architecture which basically downsamples everything and then upsample to the original image dimension, and they use up convolution. So there are different type of upsampling as well. So this is called as the transpose post convolution, right? So what uh, in transpose convolution, what is happening here is, so for input which is coming, I multiply it with kernel, but what I do is I make identical copies of pixel number 1 and multiply, and like just put whatever the multiplication is, right? So 0 into 4 is 0, 1, so 0 into 1 is basically 0. Everything that multiplies with 0 is basically placed here, right? For this location I multiply every point in this kernel and place it here, this place, right? Then this 2, then this 3, and then we actually add everything to get me the output response. Similarly up convolution also, right? So you have right, so like that you basically start filling things with maybe 0 0 0 0. Here you have 1 1 1 1 1, right? And maybe here 2 2 2 2, and similarly 3 right? Or maybe if you want to actually do it for a 3 cross 3, then it maybe becomes 0, and you just add whatever the intersecting region you were getting, so it becomes a 3 cross 3 thing. So these are basically the ways of upsampling, right? So you have reduced the original feature dimension and you want to upscale it to the original space. One thing actually they did was this, something called as a, similar to what we have learned in the skip connections. Yeah, so what they're doing is like they're concatenating the features from like the input side to the output side. So the model actually only learn on identifying uh, how does the object look like, and do not waste too much of energy in learning the overall what are the structures and everything. So we are basically giving you the whole structure. Like suppose I want, there is an image, and I want to identify maybe a person who is cycling here, right, in this region, right? There can be mountains here, maybe a river here, or like different things might be there, right? So what I want, I want my model to actually focus on only this region mostly, and extract out features from this also. And I simply want like it to have the features from other regions easily, so that like you can actually focus your energy on this region, so you can actually have a better uh, understanding of input even at the output stage. So that's why they actually put like concatenated your input part in the output as well. Yeah. So this is unit actually, right? So let us see a question. The unit is characterized by its use for a fully connected layer at the end of um, neural network, ensuring the entire image is classified into single label. So this is wrong. It's a classification task. So we are actually classifying each pixel. Unit uses a encoder decoder architecture. So this is actually your encoder, and this is your decoder, right? So you are encoding every information, like information into different regions, like into encoding your information into maybe this feature map, and using this feature map you're actually decoding back your the original segmentation mask. So it actually follows the encoder decoder architecture, right? Encoder downsamples the input image to capture context. Decoder upsamples it to provide pixel-wise segmentation map with skip connection that combine high resolution features from encoder with the upsample output. So this is correct. Uh, unit relies solely on convolution layers without any pooling operation. So there were pooling operation. That's how we are actually reducing the feature dimension. This is anyway incorrect. In unit architecture, skip connections are used to merge the output of decoder with input image, allowing model to directly compare the original input with the segmentation mask. So this is actually wrong. So skip connection actually merge input features, not image, to the output features. So this is wrong. So I think now we actually move to coding part. But if you have any doubt in this region, this part, or any of the question, just let me know. Yeah, um, so this was actually YOLO V5. So I just wanted to show you the demo for that. So this is the repo actually. If you actually go to this is a repo for YOLO. So they are actually maintaining the latest version of YOLOs which are coming up. So you can actually use this command to install this library pip install ultra lytics, and then you have different models as well. So they actually do the detection task, segmentation task, classification task. This is the pose estimation task. This is maybe counting or multi-object uh, things, right? And this is the tracking task which they're doing. So different tasks they are able to do, and it's very easy to use also. So if you want, you can actually uh, like run any of the things and see what kind of results you're getting. So now actually we will look into how. So okay, I might need to upload an image, but anyway output should be there. Yeah. So what I've done is like I've just done the inference on this image, right? I've taken some random image and done the inference, and you can see that like uh, the model is actually able to identify different like objects which are present in the image. So cars is there, bicycle is there, person is there, even truck is there, and next to each bounding box you can see a number. That is basically the class probabilities, or the how the confident the model is about that prediction. So it's 0.77 uh, confident about this is a bicycle, 0.7% that this is a person, zero point 0.9 for this is a car, right? And yeah, like very less confident about the truck, 0.49. But like anything above zero point 0.3 can be considered right. So in this case also it is basically identifying like traffic light as well. So this model was the smallest model. So this is YOLO V5S. We are actually moving to a bigger model, YOLO V5M, right? And this is YOLO V5L, right? So you can see that like the model confidence about a prediction is actually increasing. So person has a confidence score of 0.83, zero point 0.8 in medium, and zero point 0.7 in small. So you can actually see if you have sufficient data, you can go for a bigger model. So like YOLO B5L, or like uh, like even the larger one. So yeah, but in case you have smaller data, so the YOLO small or medium actually works well for you. Even in the latest version also, they have multiple type of models, like from nano to large, and you can pick uh, whichever is suitable for your application. Yeah. So this is a notebook for object counting task. Suppose you are actually building something for how many people are actually entering your shop, right? You want to do some sort of analytics between um, suppose you you're running a mall, and you want to identify which region your people are actually spending most time on, what, like which shops people are actually going, how much time, what is the average time use their customers are actually spending in different region, or different shops, or how many customers are entering your mall on a particular date, particular time, particular season. You can have this year on year data, and you can actually do analytics on top of that, so that like you can uh, attract more customers. Suppose in maybe in the rainy season or something like that, you can see that there is like drop of customers, and then you try to identify some correlation, and you can maybe give some discount on particular type of brands which might attract more customers. And if you suppose the vice versa, like you introduce some offer, like maybe 50% off on certain brand, and you want to see that like whether there is a footfall increase in your shop or not. So what you can do is like you can just place a camera on the door, and you can see that how many people are entering, how many people are exiting, and this problem actually is basically solved using object detection task. And you what you're actually doing is you have defined a line, and you're detecting in this region, like anything before line you are actually detecting, and then you are tracking the object throughout uh, the line, right? So you can see that like the counter is basically increasing in this case. Similarly, in this case also you are actually detecting the objects before it is entering your shop, and then once it enters in your shop, you actually tracks that like the same person has entered the shop, and you raise your counter to 1. So for that also you basically do, the first step is actually your detection problem. And uh, the model actually, this Yolo V11 actually gives a very good starter for that. Like only with this amount of code you should be able to generate the similar type of video. So in this case what they're doing is they are using Yolo V11 version 11, and a very small model only, right? Since it's a fairly easy task, not tracking, but these the features are very consistent, the objects are at contrast, right? So in case of difficult problems, maybe in the more real world setting, you might want to go for a higher model. Yeah, you should be able to run it and see it, yeah, for yourself. So this notebook is basically for which like for image segmentation task. I have created a unit like model, and I'm trying to train it to identify certain type of cells. So this is the data I have, so this is the image I have, and I am interested in maybe the cells which are present. So my end goal can be, can you actually identify if there are some certain type of cancerous cells or not. Before that, the first step is basically, can you actually segment out each cell with clarity, right? So each cell has different boundary, different type of shapes, and the segmentation task actually gave me this kind of segmentation mask, where wherever the one is, I am corresponding that to a cell, right? So given an input, I'm actually trying to predict the segmentation mask. Right. So since like we have seen that like whenever we are actually building a model, there are three parts which we need to take care of. First one is your data loader. How do you actually pre-process the data to be fed to your model? Second is your architecture design. How do you actually design the architecture? Are you using pre-trained architecture, or you're using you're training from scratch? And the third is basically your training loop. So the first here is uh, data pre-processing task. So this class which I have defined, slide segmentation dataset, it is basically loading all the images and corresponding segmentation masks from the directories. And what it is doing it, for each image I am opening the path, loading it, right, and resizing everything into 256 cross 256 dimension, and I'm converting it to a tensor because your PyTorch expect the output of a data loader to be in a form of a tensor. So you can actually either use uh, that torch.compose function, or you can actually directly convert it to tensor, right? This is the path I'm providing. This is uh, the instance I've created for this class, and I am using this data loader function to basically fetch me data in a batch of 4. This is the batch size 4, and I'm shuffling the data set as well. Additionally, what I'm doing here is I don't have a validation split in this case. So what I'm doing is I'm splitting 20% of the training data into the validation set, right? And I'm keeping the test data set consistent in this case. So train test split actually does that task for you. So if you actually provide it your training data, it will actually split into train and validation. It returns the indexes actually. That suppose you have 100 like samples from in the training data, so it will give you that let's keep first 80 as the training and next maybe 20 as the validation or the test. And then I'm using the storage utils the data subset. It basically sampling out the indexes which the train test split has returned me, and I'm using it as the train data. uh, so now I'm using data loader to fetch me data, right? And this is basically the visualization of image in the segmentation mask. Here I've defined the architecture of unit. So it has convolution block, right? And in it basically has an encoder decoder architecture. So you have each part I'm considering as the encoder 1, encoder 2, encoder 3. But in conceptually, it's basically the whole downsampling or the downsizing of the feature image feature is basically considered as an encoding task. So encoder 1 is basically taking out it has basically using two CNN layers, batch normalization ReLU, right? And the number of input channel is 3 and the output channel is 64, right? Similarly, the next block is basically taking input channel is 64, output channel is 128, 128, 256 again, then again like 256, 5 and 12. And this is the bottleneck layer where you have a flat representation where you have uh, like the output is basically 1024. Then I'm using this transpose convolution to actually upscale my like the feature which I have reduced, started from maybe 256 cross 256 image, right, and just scaled it down to maybe like maybe 2 comma 2 comma like 2 cross 2 cross 1024, maybe something like that. I want my output to be in the same size as my input, so output should be in the same dimension, 256 cross 256 cross 1 in our case because we are using binary segmentation task. So this basically defines your each block, right? And in the decoder part I am actually in this case, so this is what we're doing encoding. You have a bottleneck, and the decoder part what I'm doing is I'm concatenating the input as well. So decoder 4 is basically getting concatenated with the encoder at fourth place. So 4 places I have come down, and now I have to go back 4 places. In each place I am actually concatenating features from the input size. So torch.cat actually concatenate the features, right? Then I pass this to decoder, then upsample again. Decoder 3 I'm concatenating with encoder 3. Similarly, decoder 2 and encoder 2, and then you actually get the uh, final image, right? And we just pass it through sigmoid so that like the output is between 0 and 1, and use some sort of a maybe mean square error or cross entropy to basically train it. So I'm using binary cross entropy in this case using Adam optimizer, and the training loop looks like you basically start extracting out images and mask pairs from train loader. You reset your optimizer, so optimizer dot grad actually reset all the states you have. So we are basically starting fresh. So model takes images as input, output the segmentation mask. Criteria here is basically our loss function, binary cross entropy. It computes some loss. With respect to that loss, I am computing what are the gradient at each like layer. So basically decoder 4, decoder 3, decoder 2, decoder 1 bottleneck, then encoder 4, 3, 2, 1, right? And optimizers dot step is basically where I am actually updating my parameters with respect to the gradient. So you know, right, like how do you actually update it? So suppose you have weight w, so then weight, updated weight actually becomes w is actually equal to w minus your learning rate times your gradient, right? So this uh, like optimizer dot step actually takes care of that. In this case I'm using Adam optimizer. Learning rate is 1e minus 4. Generally it works well for most of the cases, right? But in case you are using any pre-trained architecture, in that setting you might want to use a lower learning rate, so that you don't uh, deviate away from already pre-learned features, or like just don't disturb them, right? So or what you can actually do is just freeze the whatever the pre-trained architecture using maybe ResNet or maybe EfficientNet, and learn few layers on top of that. So yeah, so this with this we actually start training. You can actually see the initial loss was for training loss is 0.62, validation is 0.63, and after maybe 50 epochs the training loss is 0.14, and validation loss actually becomes 0.2108. So you can actually train for more, because I don't think it is overfitting yet, uh, right? So this is how our predictions will look like. So this is the image, this is the ground truth, and these are the prediction from the model. So you can actually see it's basically able to localize things decently, right? Still making some error. See, it has missed this one, a small point. It has over predicted. This is the false positive. Here, this also is false positive. So actually, if you look into the image, this looks like something, but this is not the cell of our interest. That's why it's not been annotated. But model think, yeah, it the shape is actually looking like something. Similarly, this is also is not the object of our interest, but still model think there is something. Yeah, so with only 50 epochs, it is basically able to do some decent job, right? In this case, I don't think it is actually learning a very good shape, because there is the shapes are not actually smooth, right? So and it's all basically over predicting also. Yeah, so it is missing this region. So this cell has to be complete. It's only predicting a partial, although it's looks very difficult to predict. Just look at this in the original image. This look decent. This also looks decently well. Only issue is it makes error in making them connected. So if you are actually going for a instance segmentation task, this will be termed as one instance. So this you actually don't want. You want your boundaries to be separate. Similarly, if you can see, these are the three different cells, but the model has predicted them as one, because it's it's basically the connected components are there, and I can traverse from any point from this point to this cell to this cell. So this is basically connected. So what you want is you want actually clear boundary, so that like you can actually like classify or identify them into different instances. So that actually is a challenging task when your object boundaries are not very clear. Similarly here also you can see that like it has made it a connected thing, and if you go word it like it's actually connected. So things actually become very tricky in that case. um, yeah, so this is what unit looks like. So this I have what you've done, I've trained from like scratch. I've not used any pre-trained architecture. A further extension of this can be, instead of using like training it from scratch, you can actually extract out features from pre-trained architectures like ResNet, and use those features as in your encoder, and just learn the decoder part. So your encoder is basically extracting out good features, and you're passing those good features to the decoder, and decoder is actually making use of them and doing a good prediction. So definitely you should be able to see better results if you're actually using any pre-trained architecture in the encoder. People use efficient net as the pre-trained architecture as the encoder. So if there is something called as the efficient unit, and that is very good actually. Let me see if I can. So this repo actually implemented it, this efficient unit. So you can actually choose different type of efficient net architecture. So efficient net B5 as the encoder using here. You can actually define what is the number of classes you have right at the output, and it actually generates the architecture for you. So these things are already there, you can use them. Last, I just wanted to share with you how traditionally people used to do image segmentation. So image segmentation was actually done uh, based on what you say that original features, right? So you can see that like there are two prominent feature in this image. So one is this whitish area and the other one is a black area. So you can use the traditional clustering algorithms as well, k-mean clustering, GMMs, or mean shift segment clustering to segment out the image into two parts, right? Only issue is like since it is based on color, you can see that like the same category has been assigned to the background as well, right? Since this is black as well, so your segmentation actually becomes noisy. So I think so there is in this notebook there is a part where actually we are using this image, and we are actually trying to segment out shapes of like so this is the right. So we were basically identifying shape of different shapes, right? And like assigning different colors or maybe labels to that. So you can actually try running it as well. And here also we have implemented unit, uh, but it is a variation of version of residual unit, right? So yeah, so what is happening here is like you have torch mission dot model dot resonate 18. So it's basically the pretend architecture is present here. Now what I'll be doing is like I'm basically extracting out features from different layers. So I'm using first three layer maybe at encoder 1, next next to at encoder maybe 2, and then like eventually I'll just extracting out features from this resonate, and then I'll just have to learn the decoder part of the architecture. So we can actually will share this thing with you, and you should be able to run it. So there is something called as the dice loss. So similar to what we are actually doing in the object detection, we do the same thing, similar thing in the segmentation space as well. So what we want basically is we want your prediction and your ground truth should to overlap, right? So the dice score is basically 1 whenever it's a perfect overlap, right? And it's 0 when there is issue with the like overlapping. We don't use accuracy here because like you'll see that like the majority of the background is white, right? So if you start accuracy, if you consider this as one of the classes and compute accuracy, your accuracy will still be in the late 90s, 95, 96, right? So whenever we are actually computing accuracy, we remove this background class and then compute the accuracy. Otherwise we use dice as the loss function, or dice you can actually use as the like evaluation metric. Even IU you can use as the evaluation metric. Similarly, you can use mean square error or maybe the cross entropy as the loss function as well. Yeah. This is all I have for this week. If you guys have any doubt, just let me know. I think we have some time to discuss as well. Anyone? No doubts? Okay. Uh, then I think we will close the session here. Um, I'll share the code and the slides in, I think there's a sheet, right, where there's a YouTube link we are pasting. In the same sheet you have access to the folder, right? You can use these notebooks, run them, play around with them, and see if you can actually uh, train on your data set. So I would say for detection problem, take any image and try inferencing using Yolo. Even just try for latest models like Yolo V11 or something like that, and see how it is able to predict. For segmentation task, see if there you can actually find out any open data set and try to train a unit on top of that, and see like what challenges you're getting, or just plot your dice loss or maybe IOU and see how the model is actually learning. Then use resonate as the encoder, extract out features and do the same exercise. Just see that how you are actually going to train, what metrics you are actually optimizing learning rate, change the learning rate, change the different architecture, basically the pre-train architecture which you're using, evaluate using dice score or IOU or maybe accuracy, and see which model is doing better, how much time the model is taking, when model is overfitting. Just play around with that, and I think that actually will give you good sense of what is happening under the hood. If there are no questions, then we will close it here. And if you have any question, just put it in chat, or you can actually unmute and ask as well. Can Yolo V11 be used in medical imaging data? So for inference, I don't think it will do anything because that's completely different task. But you should be able to fine tune it. So what you need to fine tune Yolo V11 is you need images and corresponding annotation in YOLO format, right? So you need bounding box annotation for your medical data. So suppose you are doing it for maybe some sort of a tumor detection task, right? Or maybe in X-ray you have X-ray images and you are actually identifying pneumonia cases, right? So you might want to create a bounding box around your target object and save it in .txt file, I guess, right? For each image you'll have a class, uh, right, which class the bounding boxes correspond to xy width height, right, and store it in .txt file. And then you might need to create a YML file that actually points to your image and annotation or label directories. And rest, I think this library actually take care of most of the things: training, validation, uh, providing the best model. Everything has been, it takes care of that. So just try use your YOLO V11 for that. So this is basically the fine tuning paradigm. Okay. Sir, is YOLO widely used for object detection? We can, or we can use anything else. YOLO is widely used. There are two benefits of YOLO. So first one is you can actually, it basically provide you, uh, you can actually convert it for tensor RT or those edge devices. So you can play around with different model sizes. You can convert it into a smaller model, and that you can actually deploy it. So that from training to deployment path is actually very easy in this YOLO paradigm. In If the latency is not the issue for you, then there are models like Dino Deter. So DETR is one of the model which people widely use. So this is, the full form is detection transformer. Type it. So that is also very famous. So you can use that as well. But YOLO can be a good starting point because the effort to train a model on your data set is actually minimal, so you can actually get it done in maybe 3 4 hours. Anything else? Okay. uh, shall we close now if there are no more doubts? Okay, thanks. Thanks everyone for joining. See you next week. Bye bye.